Hello everyone, my name is Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on solutions, and we want to motivate this lecture by answering a very important question. That question is, what is the driving force behind the formation of solutions? In other words, why do some substances dissolve in a particular solvent while others do not? Now, chemists often refer to the rule of solubility, like dissolves like. And this principle helps explain why nonpolar solvents dissolve nonpolar solutes and why polar solvents dissolve polar and ionic solutes. However, to fully understand why a solution forms, we need to consider three key factors: entropy, intermolecular forces, and the energetics of the solution process. Let's go over each, starting with entropy. Entropy can be thought of as the measure of the disorder of the system. Now, please note this is a limited definition, and we're going to expand on it in a later chapter, but for now, let's work with this. Nature often moves towards a state in which the system is characterized by more entropy, that is, more randomness and disorder. Most of the time, the formation of a solution is accompanied by an increase in the entropy of the system. For example, when an ionic solid dissolves in water, the ions are going to go from a very ordered crystal lattice to a much more random and disordered state. Of course, this is an oversimplification, but for now, I only want to draw your attention to the fact that part of the driving force behind the formation of many solutions is to increase in the entropy of the system. Next, we want to discuss intermolecular forces. Now, this is something we covered in the previous chapter, but I'm going to do a quick review here. When forming solutions, the types of intermolecular forces between solvent molecules and solute particles play a crucial role. And that role will make more sense when we discuss the energetics of the solution process, but let's review the intermolecular forces. We have ion dipole force. This occurs when ionic compounds dissolve in polar solvents like water, where the polar molecule's positive or negative end is attracted to an oppositely charged ion. Then we have hydrogen bonding. Hydrogen bonding is when strong bonds form between a hydrogen atom attached to a fluorine, oxygen, or nitrogen, and a highly electronegative atom in another molecule. This usually leads to high solubility. Then we have dipole-dipole forces. These are present when both solute and solvent are polar. Then there's ion-induced dipole forces. This is where a charged ion induces a dipole in a non-polar molecule. Then dipole-induced dipole force, this is when a polar molecule induces a dipole in a non-polar molecule. And then last but certainly not least, we have London dispersion forces. These are temporary induced dipoles that occur in all substances, but they're the only forces in non-polar solutions. Last, we can finally cover and discuss the energetics of the solution process. So when forming a solution, it's going to be really essential to consider the energy changes involved in addition to entropy and intermolecular forces. The energy changes during this process, they can be broken down into three main steps, which are going to help us understand how solutions form. So let's go ahead and go over those three main steps. The first step deals with the energy required to break intermolecular bonds. Now, when molecules or ions are held together by intermolecular forces or chemical bonds, they have lower potential energy. To separate these particles, energy is needed, making this process endothermic. It absorbs energy. So for example, in potassium chloride, ionic bonds hold the potassium cations and chloride anions together. to dissolve potassium chloride in water, we have to first overcome these solute-solute attractions by breaking these ionic bonds. And this requires energy. So for this first step, it's going to be endothermic, and I'm going to denote that change in enthalpy as delta H1. The next step deals with energy required to separate solvent molecules. These solvent molecules are also held together by intermolecular forces. To allow solute particles to mix with the solvent, these solvent-solvent attractions have to also be overcome. And this makes this process endothermic as well. It requires an absorption of energy. And we're going to denote that as delta H2. So these first two steps, the energy required to break intermolecular bonds for our solute and the energy required to separate our solvent molecules, are both endothermic. They both absorb energy. The third and final step requires us to discuss the energy released when the solute and solvent mix. So when solute particles and solvent molecules come together, new intermolecular attractions form. And this is going to release energy and lower the potential energy of the system. This process is actually exothermic. It releases energy. So in the case of potassium chloride dissolving in water, the potassium cations and chloride anions interact with water molecules, forming ion dipole attractions and releasing energy as the new interactions stabilize the system. We can denote the change in enthalpy for this step as delta H3. Now, these three steps can be summarized by the overall energy change during the solution process, known as the heat of solution. And the heat of solution is just the total energy change when a solute is dissolved in a solvent. So we have our first two steps, delta H1 and delta H2, which are endothermic steps because they involve breaking solute-solute interactions and breaking solvent-solvent interactions. Then our last step is exothermic, and we denote this by delta H3. This is exothermic because we're forming new solute-solvent interactions. Now, for a solution to form, the energy released when the solute and solvent mixed has to be enough to compensate for the energy required to separate the solute and solvent particles. If the energy balance is favorable, then the solution forms. In reality, though, these processes don't happen in distinct stages, but they occur simultaneously as solute and solvent particles interact. And this simultaneous interaction is really crucial for the formation of stable solutions. So the key takeaway here is that the solute-solvent attractions must be comparable in strength to the original solute-solute and solvent-solvent attractions for a solution to form. With that, let's go ahead and tackle some practice problems together. This problem says, determine the predominant intermolecular forces between solute and solvent in the following solutions. Our first solution is of hexane dissolved in octane, and we're given the molecular formula for hexane, C6H14, and for octane, C8H18. Now, both of these molecules are hydrocarbons, just carbons bonded to hydrogens. And that helps us determine that both hexane and octane are nonpolar because all hydrocarbons are nonpolar. Therefore, the only intermolecular attractions present between hexane and octane are going to be London dispersion forces. Let's go ahead and take a look at our second solution here. We have potassium sulfide in ethanol, and we're given the molecular formula for ethanol, CH3CH2OH. We have an alcohol group here. Now, potassium sulfide is ionic and ethanol is polar. Ethanol molecules are actually held together in the liquid phase by hydrogen bonding, but there is no hydrogen bonding between the ions of potassium sulfide and ethanol. Now, when we have an ionic compound that dissolves in a polar solvent, the ions are going to dissociate. The potassium cations become solvated by the negative end of ethanol, and the sulfide anions become solvated by the positive ends. And so what we're going to have here are ion dipole forces that are going to predominate in the solute solvent forces in this kind of solution. So let's write that down, ion dipole forces. And we can picture this by drawing our potassium cations that are going to be dissociated in solution. They're going to interact with the negative ends of our ethanol, so the oxygen of our ethanol molecule. And then our sulfide anion is going to interact with the positive ends of our ethanol molecule. So it's going to look something like this. There's a partial positive charge associated with the hydrogen in ethanol and a partial negative charge associated with the oxygen atom in ethanol. So there you have it. We solved this problem. Now we get to move into our next objective, which is going to deal with the composition of solutions. Chemical reactions often take place when two solutions are mixed. To perform stoichiometric calculations in such cases, we need to know two things. First, we need to know the nature of the reaction, and that depends on the exact forms the chemicals take when they're dissolved. And the second thing we need to know is the amounts of chemicals present in the solutions, and that's usually expressed as concentrations. Now, the concentration of a solution, it can be described in many different ways. At this point, we're going to consider only the most commonly used expression for concentration, and that's molarity. Then we're going to expand on the other ways that we can describe concentration. Now, molarity is defined as the moles of solute per volume of solution in liters. And we can write that as N divided by V. Now, chemical labs, they often purchase concentrated solutions which have to then be diluted prior to use. These concentrated solutions, called stock solutions, they take up less space in a chemical stockroom than more dilute solutions containing the same amount of solute. So that's why they buy stock solutions that they can then dilute for specific uses. Now, dilution is a really important process in chemistry, especially in preparing solutions for experimental procedures. It often involves adding a solvent, usually water, to a concentrated solution to decrease its concentration. Molarity, again, the number of moles of solute per liter of solution, is a standard unit of concentration in chemistry. When a solution is diluted, the total amount of solutes in moles, that remains constant, but the volume of the solution increases, and that results in a lower molarity. The process of dilution, it can be described by this equation here. We have the molarity of our concentrated solution multiplied by the volume of our concentrated solution. This is going to be equal to the molarity of our diluted solution multiplied by the volume of our diluted solution. This relationship shows that the product of the initial concentration and volume is equal to the product of the final concentration and volume. And this principle is so important because it ensures the conservation of the number of moles of solute during the dilution process. Notice that when a solution is diluted, the volume changes and the concentration changes, but the number of moles of solute does not change because all we have added is more solvent. Now, in this discussion of dilution, we covered molarity, but we also want to cover other units of concentration. We said again, Molarity is the number of moles of solute dissolved in 1 liter of solution. But what about these other units of concentration? Let's start with molality. Molality is the number of moles of solute per kilogram of solvent. Unlike molarity, it depends on the mass of the solvent, not the volume of the solution. Molality is particularly useful in thermodynamic calculations, such as those involving boiling point elevation and freezing point depression, because it is independent of temperature changes. We're going to use molality in our last objective where we discuss colligative properties. We also have mass percent, which is sometimes called percent by weight. This is the mass of the solute divided by the total mass of the solution multiplied by 100%. It expresses the concentration of a component as a percentage of the total solution mass. This unit is commonly used in industry, manufacturing, and pharmaceuticals to specify the concentration of ingredients in the product. Then we have mole fraction. Mole fraction is the ratio of the number of moles of a component to the total number of moles of all components in the solution. It is a dimensionless quantity. Mole fraction is used in calculations involving partial pressures and also colligative properties, and it's especially useful in gas mixtures and ideal solutions. Then we have parts per million. Parts per million is a measure of concentration that expresses the number of parts of solute per million parts of the solution. It is equivalent to milligrams of solute per liter of solution in the case of water. Parts per million is widely used in environmental science, in water quality testing, and also in pollution measurements to express trace concentrations of substances. Last, we want to discuss parts per billion. Parts per billion is a measure of concentration that expresses the number of parts of solute per billion parts of the solution. It is equivalent to micrograms of solute per liter of solution in the case of water. Parts per billion is used to measure extremely low concentrations of pollutants, contaminants, and trace elements in environmental studies, particularly in air and water quality assessments. With that, let's go ahead and jump into some practice problems. This first problem says, what is the molality of an aqueous solution containing 3% hydrogen peroxide by mass? Now, whenever you're asked to express concentration in terms of a particular unit, you should begin by writing the formula for that unit. The formula for molality, which is what we're being asked for, is equal to the number of moles of solute divided by the mass of the solvent in kilograms. Now that we have that written, the second thing we want to do is write what we are given in this problem. We're given that the mass percent of hydrogen peroxide by mass is 3%. Mass percent is defined as the mass of A divided by the mass of solution multiplied by 100%. So here for hydrogen peroxide, it is the mass of hydrogen peroxide divided by the mass of solution multiplied by 100%. Now, knowing that the mass percent of hydrogen peroxide in this solution is 3%, the easiest approach is to assume that we have 100 grams of solution. That way we can say that the mass of hydrogen peroxide is equal to 3 grams of hydrogen peroxide, and that the mass of the solution is equal to 100 grams. Therefore, 3 grams divided by 100 grams multiplied by 100% gives us 3%. And that aligns with the problem saying that we have 3% hydrogen peroxide by mass. Now, if we know the mass of hydrogen peroxide and we know the mass of the solution, we can go ahead and determine the mass of the solvent. How? Well, the mass of solution is equal to mass of the solute plus the mass of the solvent. We know the mass of the solution, we know the mass of the solute. We can rearrange this expression to solve for the mass of the solvent. It's going to be equal to the mass of solution minus the mass of the solute. So it is going to be 100 grams minus 3 grams, and that is going to equal 97 grams. The mass of the solvent, and that is 97 grams. In molality, our denominator is the mass of solvent in kilograms. So we want to do a quick conversion of 97 grams to kilograms. That is going to equal 0.097 kilograms. We just have to divide grams by 1,000 to get kilograms. So now we know our denominator. It is equal to 0.097 kilograms. Our next step is to figure out what the numerator is going to be so we can calculate molality. Now the numerator is number of moles of solute. Now we know our mass of solute is equal to 3 grams. We can use molar mass to convert 3 grams of hydrogen peroxide to moles of hydrogen peroxide. The molar mass for hydrogen peroxide is that 1 mole is equal to approximately 34 grams of hydrogen peroxide. If we plug this into a calculator, we're going to get that we have 0.0882 moles of hydrogen peroxide. Now we know the number of moles of solute, and we know our mass of solvent in kilograms. We can calculate molality by just plugging in the values. Our numerator is 0.0882 moles of hydrogen peroxide, and our denominator is 0.097 kilograms. Plug this into a calculator, and we're going to get that our molality is 0.909. And that's our final answer. Now we can write this as 0.909 molality, or we could write it as moles per kilogram. And there we have it. That's that first practice problem. Let's tackle the next one. This problem says a 0.750 molar sulfuric acid solution at 25 degrees Celsius has a density of 1.046 grams per milliliter. What is the concentration of this solution expressed in molality? Now, the first thing we want to do is we want to write down the formula of the concentration term we're trying to figure out. This is going to allow us to identify which terms we need to determine. So in this case, we want to express the concentration in units of molality, and molality is equal to the number of moles of solute divided by the mass of the solvent in kilograms. Now that we've written this down, we also want to write down what we're given in this problem. This problem tells us that the molarity of the solution is equal to 0.750. Molarity is defined as moles divided by the volume of the solution. So we can write this as 0.750 moles divided by liter. Now, since we're given the concentration and molarity, the easiest approach for this problem is to assume that we have 1 liter of solution, which means that our number of moles is equal to 0.750 moles of sulfuric acid, and our volume of solution is equal to 1 liter. Now, we know the number of moles of solute, and the only thing we need in order to determine the molality is the mass of the solvent when there is 1 liter of solution. To help us do that, we're going to take advantage of the fact that we're also given the density of this solution. The density of the solution is given, and we can use that to find the mass of 1 liter of solution. In order to do this, let's write down our definition for density. Density for a solution is equal to the mass of the solution divided by the volume of the solution. If we're trying to figure out mass of the solution, we can rearrange this equation. Mass of the solution is going to be equal to the density of the solution multiplied by the volume of the solution. The density of the solution is 1.046 grams per milliliter. And the volume of the solution we said is 1 liter, which is equal to 1,000 milliliters. And we want to write it as 1,000 milliliters so our units cancel out and we get our mass of our solution in units of grams. If we calculate this, we're going to get 1,046 grams for the mass of our solution. Now, notice that the mass term that we calculated is the mass of the solution, not the mass of the solvent. But to calculate molality, we need the mass of the solvent. Mass of our solvent is going to be equal to the mass of the solution subtracted from the mass of the solute. Okay, but we don't have the mass of the solute. That's okay. We have enough information to calculate it. We know the number of moles of our solute, 0.750 moles of sulfuric acid. We can convert this to mass of solute using molar mass. Now, what is the molar mass for sulfuric acid? 1 mole of sulfuric acid is equal to about 98 grams of sulfuric acid. If we plug this into a calculator, we're going to get that the mass of our solute of sulfuric acid is 73.5 grams of sulfuric acid. Wonderful. So we have our mass of our solute, and we just previously calculated the mass of the solution, which was 1,046 grams. Let's go ahead and calculate the mass of our solvent by subtracting those two quantities. It's going to be 1,046 minus 73.5. This is going to be approximately 972 grams, and this is going to be equal to 0.972 kilograms. Remember, in molality, the denominator is the mass of the solvent in kilograms. Now we know the number of moles of solute, 0.750. And now we know the mass of the solvent. We can easily calculate the molality. So let me erase some of this work right here, and we're going to plug it into our equation. Molality is equal to 0.750 moles of sulfuric acid divided by the mass of our solvent in kilograms, which is equal to 0.972. If we plug this into a calculator, our molality is equal to 0.771. And there we go. We solved our second practice problem. And with that, we can move into our third objective, where we're going to discuss the effects of temperature and pressure on solubility. When we're considering the effects of temperature and pressure on the solubility of substances, it's important to understand how these factors influence the interactions between solutes and solvents. The first thing we want to discuss is the effect that temperature plays in determining solubility. For most solid solutes in liquid solvents, an increase in temperature generally leads to an increase in solubility. This occurs because higher temperatures provide more kinetic energy to the molecules, allowing the solute particles to more readily break apart and mix with the solvent. A good example of this is the way sugar dissolves more quickly in hot water compared to cold water. However, the relationship between temperature and solubility is different for gases dissolved in liquids. As temperature increases, the solubility of gases in liquids typically decreases. This inverse relationship occurs because the higher kinetic energy at elevated temperatures makes gas molecules more likely to escape from the liquid into the gas phase. This is why carbonated beverages lose their fizz more quickly when they warm up. The dissolved carbon dioxide gas escapes as the temperature rises. Now, pressure also significantly affects the solubility of gases in liquids, as described by Henry's law. This law states that the amount of gas that can dissolve in a liquid is directly proportional to the partial pressure of that gas above the liquid. In simpler terms, increasing the pressure of a gas over a liquid pushes more gas molecules into the solution. The proportionality constant in this relationship is known as Henry's law constant. So for example, carbon dioxide is dissolved in soft drinks under high pressure, which is why they remain carbonated until you open the beverage, releasing the pressure and allowing the gas to escape. Now, this idea is closely related to vapor pressure, which is the pressure exerted by the vapor of a liquid when it is in equilibrium with its liquid phase. The relationship between gas solubility and pressure can be expressed by this equation right here, where the solubility of the gas in the liquid depends on Henry's law constant and the partial pressure of the gas. Understanding this relationship is important in applications ranging from beverage carbonation to industrial gas-liquid processes. And ultimately, by considering how temperature and pressure interact with solute-solvent relationships, we gain a clearer picture of how solutions form and behave under various conditions. And with that, we're going to end this video here. In the next part, we're going to finish up this chapter and discuss colligative properties. I hope this video was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.